Good day. My name is Bob Moskaitis. I'm the Technical Director of Mintech International Pyrogenics Group, and I'm here today to share with you a presentation that I made earlier this year at IMAPS in France. The Advanced Thermal Management Workshop deals with exactly the issues that face the application community today, and that is how to take heat away from increasing power density devices. So we're going to spend the next 15 minutes in going through those slides, and at the end you'll have time to ask me questions. Our agenda for today will be, we'll spend a brief amount of time looking at the background of this problem area. We'll discuss our recent advances in the area of metallization technology, which allows us to contact our material directly to a device. We'll examine two case studies that are relevant, one a two-dimensional application and one a three-dimensional heat spreader application. Then we'll look at the increasingly important area of CTE analysis before we finally make our conclusions. The trend, of course, is that more effective thermal management solutions are required, and this is so in both defense and commercial applications. And we find this need covers a wide range of application areas, all the way from laser diodes to electronic packaging. You probably have read a lot about carbon recently. It seems like it's enjoyed a renaissance in the scientific community, and rightly so, because carbon is the element with the highest melting point of all, over 3,000 degrees Kelvin. Carbon nanotubes has been something which has been in the literature most recently, and in fact it may offer a thermal management material for the next century, but you'll be hard-pressed to find commercial applications right now. We have a material that we manufacture in our site in Easton, Pennsylvania each and every day, and we believe that our new form of pyrolytic graphite, Pyroid HT, is the thermal management material for this decade. We make our material, it's a synthetic pyrolytic graphite, at very high temperatures via a chemical vapor deposition process. The resultant material is extremely crystalline and extremely pure. Through a compressive annealing step, we are able to manufacture a material with a 1700 watts per meter K thermal conductivity in two directions. Of course, graphite is an anisotropic material, and that's important when we look at engineering our material to meet the application needs. It is a lightweight material with a density only 25% that of copper, and our custom production process allows us to manufacture this material, which machines very easily, in thicknesses from 10 mils to 2.5 centimeters. The metallization technology that we've developed also allows us to contact our material to a wide variety of devices. This further illustrates the thermal conductivity measurements that we've done with both laser flash diffusivity and also ASTM D5470 techniques. In the XY plane, it is 1700 watts per meter K repeatably. In the Z plane, it's a near insulator, having only a thermal conductivity of 7 watts per meter K. Comparison to standard pyrolytic graphite is stunning in that we have over a 4 times increase in our high conductivity plane, and in fact approaching diamond at 2000 watts per meter K. Metallization development was very important to ensure that we have an acceptable bond strength. So the work that we've done has been verified by an outside testing laboratory which has conducted Sebastian pool test, which is a common test that allows us to test various metallization schemes using the mill standard 883. The results of that metallization bond strength testing verifies for us that in using a wide range of metallization schemes, using a titanium first layer that allows for strong adherence to the pyrolytic graphite, a barrier layer, which could be either nickel or platinum or nickel chrome, and finally a gold layer, which allows for extremely good adherence to electronic devices. We were able to offer both an acceptable fracture stress and shear failure load that would make this material readily acceptable for a wide variety of electronic uses. In addition, we've been able to test the compatibility of selected solder types. And the idea here was we wanted to simply see whether we were not generically compatible. We are. And we would customize any additional work depending upon the particular customer application. We proceeded to then take the materials that we now can metallize and we can adapt them to an electronic device. We're going to look at two different case studies, the first of which is a two-dimensional laser diode case, which represents a wide area of application need. We not only have done thermal modeling through the thermal engineering expertise of Omega Piezo, but we've also been able to verify the thermal modeling through experimental devices which tested our material, Pyroid HT, versus copper molybdenum or copper. Here's an example of the thermal modeling that we have done. We have a laser diode located here, which has a constant heat flux of 200 watts per square centimeter. And we have a heat sink that's operating at 30 degrees C. The material, in this case Pyroid HT, has been engineered such that the high conductivity directions are in the Z direction through and in one of the XY directions to enable the heat to be rapidly taken from the laser diode to the heatsink. If we can accomplish this, we'll be able to improve both the effectiveness and the efficiency of the laser diode. The results of the thermal imaging are rather dramatic in that on this side we have a copper molybdenum, which is a 160 watt per meter K material, versus the Pyroid HT pyrolytic graphite at 1700 watts per meter K. And of course, as you notice, it's a very uniform and a very cool interface between the laser diode and our material, as opposed to the more traditional and hotter zone that you experience with either copper or copper molybdenum. Quantitatively, what we have observed is a 70 degree C reduction in the junction temperature. This, of course, is significant for an industry where 10 degrees C is something that is considered notable and could result in either an increased lifetime for the device or the opportunity for increased power at constant junction temperature. Those degrees of freedom are illustrated in this graph, where we compare the results for the Pyroid HT, for a copper molybdenum, and for a copper heat spreader arrangement. And this indicates that for a constant junction temperature, for example 100 degrees C, we're able to increase the power output by over 50% compared to traditional materials. So we believe that Pyroid HT pyrolytic graphite offers a degree of freedom for the thermal management designer that did not exist before. We also understand that certain applications require a three-dimensional heat spreader. And because of the engineering capabilities of this material, we're able to manufacture a near isotropic three-dimensional heat spreader. And so we'll look at the results for such a case. Here, once again, we're able to enjoy over a 30 degrees centigrade reduction in junction temperature using a three-dimensional engineered layered approach, which has a resulting average isotropic bulk conductivity of 1350 watts per meter K. For either the two-dimensional or three-dimensional case, an additional engineering component, the CTE, is a very important analysis point. And in looking at the benefits of pyrolytic graphite versus diamond, for example, one of the key properties that you must consider is the modulus of elasticity. And in fact, the conformance capability of pyrolytic graphite exceeds that of diamond to a high degree. Whereas diamond is brittle, the mechanical stress elasticity of pyrolytic graphite allows it to conform to the underlying substrate over a wide range of temperatures to a much better degree. And so we believe this improves the capability of the material to be a very effective heat spreader. If we look at the die spreader material stress results, what you find is that for pyrolytic graphite in silicon with Pyroid HT, you have an order of magnitude lower stress than that which is experienced between diamond and silicon. This presents a number of options for the utilization of pyrolytic graphite, Pyroid HT, in these applications. We can use it as a base material. We can metallize the surface, either a single surface or all surfaces, with a wide array of metallization schemes. We can solder it using a wider range of solders that are commonly used. We can mount it as is if you use a mechanical device, or with the metal reinforced backing, or most recently, we've also developed an epoxy fiberglass reinforcement technique. So in conclusion, we believe that the intrinsic anisotropy and strength limitations have been addressed using an engineered orientation in the fabrication approaches with our Pyroid HT pyrolytic graphite. We've developed an optimization model which illustrates the effectiveness and efficiency of this material as a heat spreader. The elastic modulus, we've noted, is just as important as CTE for the mechanical compatibility between the spreader and the die materials. And finally, we hope to demonstrate for you that Pyroid HT pyrolytic graphite heat spreaders are a very cost-effective alternative to diamond and copper. I'm happy that you've been able to join us for this brief amount of time. You'll find that this presentation is on our website and available to you to be downloaded. And we'd be very happy to answer any questions that you might have for me personally, either now or at your convenience later. Thanks for joining us today. Again, my name is Dr. DrBobMoskaitis, working for Mintech and our Pyrogenics group. Thanks for joining us today to discuss thermal management. I'm available for any questions, either now or at your convenience. I'd be more than happy to help you as you look to utilize pyrolytic graphite in our Pyroid HT in your application. Thank you.